Hi, everybody. I just wanted to make a quick video to go along with your reading that reviews a couple of things that we talked about in class, but then also goes into a little bit more detail with Coulomb's law. The reading is a little mathematical, a little dense, and I know some of you appreciate having something to go along with it, so hopefully this video does the trick. So first, a quick review. Remember that the unit of charge, when we're talking in electricity, we're always talking about transfers of charge, right? We rub things together, they transfer charge. There's a lot of different ways to transfer charge. And when we're transferring charge, we're really talking about transferring electrons between objects. You become positively charged generally by losing electrons, and you become negatively charged generally by gaining electrons. Since electrons are pretty tiny, they're very lightweight in terms of the other particles that are in an atom, like protons and neutrons, and they're on the outside of the atoms. They are the ones that are easy to transfer. And so you don't like steal a bunch of protons from something to become positive. You lose some of your electrons to someone else, and that leaves a deficit of electrons that makes you positive. Now, the unit of charge is the Coulomb, named after a French physicist who did a lot of foundational research on electricity and actually figured out how to measure the force between charged particles. So I'll write that here, Coulomb, Coulomb, and it's abbreviated as a C. So we'll say just like we use kilograms for mass, we use C for coulombs. The variable that we use to describe charge is often the letter Q. So it's a capital Q or it's a lowercase q. And so you might say, I have a charge Q equal to -6 times 10 to the -3 coulombs. That would be -6 millicoulombs. And that's actually quite a bit of electrons. Since electrons are so tiny and they carry so little charge, you really have to transfer a lot of electrons to accumulate this much negative charge. Just as a reminder, the electronic charge, which is the charge on the electron and the proton, and it's the smallest unit of charge for all practical purposes that we can deal with in day-to-day life, there is something tinier called a quark, but they're very hard to isolate. So electrons are considered the fundamental unit of charge. When you see charge, being transferred, you're never going to have like 2.5 E, you'll have like 3 E, 10 E, a billion E. You'll always have whole multiples of the electronic charge because you're always transferring whole numbers of electrons between objects. So that equals 1.6 times 10 to the -19 coulombs. So just think about how small that is. And remind yourself too that a proton carries a charge of positive E, and an electron, even though it's considerably less massive, carries the same charge as the proton, but just negative. So that's a rundown of the basics. Now, Coulomb's law. Coulomb's law states that if I have two charges, so let's say two little point charges, we tend to call them point charges, Q1 and Q2, and they're separated by some distance, let's call it R. And that would be, if they had any size, that would be the center to center distance, just like we treated gravity. This looks really similar to like when we're talking about two masses and they attract one another. And the force between them is given by K, which is a constant. It's not the spring constant. It's a whole other constant. I'll give you the units and the value. It's a really big number. And then times Q1, Q2 over R squared. And so if I were to graph this, F versus R, it would be an inverse square law. Put down like that. Okay, now the first thing is, this looks real similar to gravity, right? One of the biggest differences is the magnitude of the constant here. The gravitational constant is super tiny. The electrical constant is really big. K equals 9 times 10 to the 9th Newton meter squared per Coulomb squared. Just like G was Newton meter squared per kilogram squared, because I had kilograms up here, this is Newton meter squared per Coulomb squared to make the force come out in newtons. And you'll notice it's really big. And that's why electrical forces manifest in everyday sorts of everyday size things so much more strongly than gravitational forces. Let's see. What else? Oh, so another important thing that we have to do differently between electricity and gravity is that mass was always positive and gravity only attracted. Electrical forces can be attractive or repulsive. And so they can push things away, they can pull them in. We know that like charges, whether they're both positive or both negative, would repel, and opposite charges, positives and negatives, would attract one another. And so what A really confusing thing that can happen is we know force is a vector, and we tend to think of like vectors point in a positive direction, or if they point in a negative direction, and we usually define a positive or negative direction. Well, if you put in the signs for the charges, and let's say you have opposite charges, right? A positive and a negative, you're going to wind up with a negative force. And that negative force doesn't mean it points in the negative direction necessarily. It just means that the charges had opposite sign. Whereas if I put in two positives or two negatives, it would be positive because when you multiply them, you'll get a positive number. And so to avoid that whole level of confusion, we just don't use the signs. So when you're operating with Coulomb's law, the force that you're calculating is really the magnitude of the force, not the actual direction. The direction you have to work out in your head based on what the relative signs of the charges are and like which way you think it's going to get pushed based on the situation that you're studying. And so sometimes you'll see this written like this, F, the magnitude or the absolute value of the force is equal to K times the absolute value of Q1 times the absolute value of Q2 over R squared. And that's fine. I'm not going to write it that way because it gets really cluttered when you're writing it that way, but I'm always thinking that. So when Mr. BH and I write that, when we write this, we mean that. Never put the signs in when you're dealing with electric forces. It makes for too much confusion. Okay, so let's do some examples and see if we can see how this works out. So I'm going to erase this. I'm going to erase my inverse square law. I'm going to keep my picture up there. Let's just calculate the force between two things. Let's calculate the force between, let's say I have this charge over here. Let's say Q1 is, let's say Q1 is negative. I'll keep this charge that I had right over here, negative 6 times 10 to the negative 3 coulombs, minus 6 millicoulombs. And let's say Q2 is positive, and it's plus 2 times 10 to the negative 3 coulombs. And let's say that they're separated by a distance of 3 centimeters, so 0.03 meters. That's their center to center distance. Okay, what's the force between them? So we can just loosely calculate the force between them. That's the first thing we can do. So let's just do that. 9 times 10 to the 9th Newton meter squared per Coulomb squared times, and remember, I don't put the sign in, so it's 6 times 10 to the negative 3 coulombs times 2 times 10 to the negative 3 divided by the distance between them squared, which is 0.03 meters squared. And if it wasn't so late, I'd probably be able to do this in my head, but 1.2 times something, right? So 9 e to the 9th times, calculator, quit mode. Okay, good. 9 e to the 9th, and you can program K in your calculator just like we program G. 6 e to the negative 3. Times 2, and remember I didn't put the signs in, divided by 0.03 squared, and I get 1.2 times 10 to the big. I get 1, 2, 3, 4, 5, 6, 7, 1.2 times 10 to the 8. That's a really big force. That's huge, right? That's because this is actually quite a lot of charge. And because of the large value of K, and also the fact that this is a pretty decent amount of charge, and that's a really tiny distance, you're going to get a really strong force out of that. So that's interesting how you can see the scale of these things. Okay, let's do something a little different. Let me erase this now. Now I want to really start paying attention to direction. Okay, we know by Newton's third law that if I still have my picture of Q1 and Q2, that's the force Q1 exerts on Q2, and it's also the force that Q2 exerts on Q1. Even though they have different amounts of charge, just like the force of you on the Earth is the same as the force of the Earth on you, the force of Q1 on Q2 is the same as the force of Q2 on Q1. They're just going to push in different directions depending on the relative signs of the charges. In the case before, that was an attractive force because the particles were opposite in sign. Let's look at another situation. Let's say I have a charge over here. And let's say that charge is Q equals -2 times 10 to the -6 Coulomb. So it's a -2 microcoulomb charge, and it's just sitting there. And let's say it's sitting there at point, I'm going to call that point A, just sitting there. So QA is sitting there. Now let's say somewhere over here, a distance of 0.2 meters away, so like 20 centimeters, I have another charge, and it's also negative. And it's QB at point B, this is QA at point A, is, let's say that one's -3 times 10 to the -6 coulombs. And let's say I'm interested in the force on QA. Which way is QA going to go? So which way would QB push QA? Well, QB is negative, QA is negative, and I know negative charges repel each other. So QA would be repelled by QB, and the force on QA would be like this. And, people have different ways of writing the notation. I tend to write this as the force on A due to B. So that's the force on A due to B, it's that way. Now the force on B due to A would be that way, and it would be on this charge. And so it's really important to think about which charge you're wondering, what's the force on this charge? Be really specific. I want to know the force on QA, so the force is to the left. If I wanted to know the force A exerted on B, the force would be to the right. Okay, let's calculate FAB. FAB is going to be K, which is 9 times 10 to the 9th Newton meters squared over Coulomb squared, times, again, I don't put in the sign, so 3 times 10 to the -6 times 2 times 10 to the -6, and then divide by 0.2 meters squared. Hopefully this comes out a little less big. Let's see. Clear. 9 e to the 9th times 3 e to the -6 times 2 e to the -6 divided by 0.2 squared, and I get 1.35 newtons. Okay, and I like to personally put a little note to myself. You could call that negative 1.35 newtons. I just put a little arrow telling myself which way it goes. Okay, now, let's say I came along and I put another charge over here at point C. And let's say that charge was also negative. So I'm going to put, now let's say it was positive. I'm going to put a positive charge over here. I'm going to call it QC, and it's at point C. And let's say it's equidistant. So let's say it's also 0.2 meters away from charge A. And its value, QC, is equal to, let's say, positive 1 microcoulomb, 1 times 10 to the -6 coulombs. Now, what is going to happen to QA? I know QA is feeling a force to the left from QB. And now I have this other charge over here that can also exert a force on QA. And likewise, QA can push on QC and QB can push on QC, but I'm interested in QA. So I know QA is being pushed away with a force on A caused by B. Which way is QC going to push on QA? Well, QC is positive, QA is negative. So if I were QA and I was seeing QC over there, I'd be like, wow, there's positive charge. I'm going to go towards it. I want to go over there. I want to get over there, but I'm not allowed to because I'm stuck over here. But so QC would be pulling on me towards it. And so I have a second force that's acting. I'm going to write this one below so I can write my other one. This was FAB. And I also have acting on QA, and I'm going to draw it above it. I also have FAC. Now, I don't know the relative values yet. I know it's going to be less because this was between a 2 and 3 microcoulomb charge, and this is only between a 1 and 2 microcoulomb charge. So I could, if I wanted to, I could actually make this a little shorter and be accurate. So let's calculate FAC. FAC is going to be K, which is 9 times 10 to the 9th, times QA, which is still 2 times 10 to the -6 coulombs. It's really -2, but I don't put the minus in. And then times 1 times 10 to the -6 coulombs. And then I divide that by 0.2 meters and I square it. And if I calculate that, here's a little trick. Since everything is the same, I can just take this number divide by 3, and then multiply by 1. So that's what I'm going to do. I get 0.45 newtons. And that force is also to the left. Okay, so I have a second force also to the left. What do I do when I have two forces in the same direction? And I know you're thinking to yourself, I should add those forces. So let's get the total force on A. So the total force on A is going to be equal to F on A caused by B plus F of A caused by C. And I know to add them because they're in the same direction. If this had been a negative charge, FAC would have been that way. What would I do? I would subtract them. Exactly. So FAB plus FAC equals FA. And so that's going to be FA equals 1.35 newtons plus 0.45. Now you might be wondering, these are to the left. Should I make them negative? You can make those both negative and then just like add the two negative forces and get a negative force. I tend to just kind of be directional and then say it's to the left or to the right at the end when I do these. I don't really make them positive or negative, but you could do it that way if you want. It would be totally right. So 0.45 plus 1.35 I should be able to do is 1.8. So my answer is 1.8 newtons to the left, or negative 1.8 newtons if I defined negative as the right as left and right as positive, or just 1.8 newtons that way. So these two charges together exert a force on QA, and we combine them just as if they were each their own little private pair of charges. For example, if I were looking for the force on C, how would it change? So let's say I were now concerned with C. I'm not going to calculate it, but let's just work out the direction. Here I am as charge C. Which way would A pull on me? If I were C, I'd be like, oh, a negative charge. I want to go that way, right? And then I'd see that negative charge too. This charge doesn't block that charge. They both exert a force on this charge here. So QA would feel pull toward, QC would feel pull towards A, QC would feel pull towards B, and I'd have two forces. But remember, in calculating these forces, I'd have to use a bigger distance. All right, so I hope that gave you a little bit of insight into Coulomb's law. You could get fun too with angles, right? Like if I had instead put a charge down here, right? If this charge instead, I could move it down here. That second force would have been down. So you would have had a vector like this and a vector like this. Think about how you would combine those. Okay, we'll see you soon. Bye.